Hello everyone, I'm Rohit Kumar Singh, the TA for this course, uh, Experimental Physics 2, and this is the seventh live session. And today, uh, we will discuss some more concept on optics, basically wave optics. We will study some experiment which are based on the interference of light wave and how we can calculate the wavelength of light using those experiments. So uh, let's start. So I'll just quickly summarize some of the concepts and formulas about interference. So interference is a phenomena uh, in which two or more waves form a composite wave uh, and which is based on the principle of superposition. Uh, Either the composite wave uh, will be a result of constructive interference or destructive interference, which will lead into increased magnitude or decreased magnitude. Sorry, amplitude of the composite wave. So, suppose there are two waves uh, like this. Okay, this is going this way, and suppose another wave is coming from this way. Now, these two will meet at a point, and the result will be that uh, there will be a composite wave which will be given by, suppose, like this. So you see here the magnitude of the wave got increased. Okay, so this is a constructive interference. Okay, and also it might happen that uh, uh, if it will depend on the phase difference between these two waves, that the wave will cancel each other, and then we'll have a destructive interference, like so. There will be no wave at all, or the magnitude will be reduced like this. Okay, so these are the scenarios which can happen, and uh, so this is uh, this interference is based on the superposition formula. So you superimpose these two waves, and what you get is the uh, interference wave or composite wave after interference. So I will not go much detail into interference. Rather, I'll talk about one experiment which is based on interference called Young's double slit experiment, or YDSC. Okay, so here uh, in young double slit experiment, you have a light source. It should be monochromatic, that is, having only one wavelength. Then you have two narrow openings called slit, okay, S1 and S2. The distance between them should be D, and then at the distance capital D, you have a screen, okay, and this is O. So what will happen is that uh, there will be two light ray coming, one from this slit and one from this slit, suppose at this point P. Okay. Now since uh, this second light S2P, second ray, has traveled more distance, so this is the delta, right, has traveled more distance than the S1P, so S2P is greater than S1P, and hence there will be some uh, phase difference between the two light rays. And so since I told you that depending on the phase difference there will be constructive or destructive interference, so at different position on this screen there will be constructive and destructive interference. And so you will have somewhere you will have white, uh, I mean you have uh, white region, and then you have dark region, then bright region, dark region. So that is called a fringe pattern or interference pattern. Okay. So there is a condition. So when there will be constructive and destructive interference, and that condition is given by delta is m lambda, where lambda is the wavelength of light, 0 plus minus 1 plus minus 2, like this. And so this is for constructive. Okay, and for destructive interference the condition is m plus half lambda, where m is again integer, and this is destructive. Okay. uh, so and also you can calculate the uh, and also this deviation is simply, since this angle is very small, so this distance is very small, delta can be written as d sine theta. Okay, and that can be since the theta angle, this is the theta angle, this angle is theta. Okay, and this is very small, so this can be written as d tan theta due to small angle property. And then you can write, so tan theta is just, so suppose this is the distance y where the fringe pattern observed, then tan theta is just y by d. So, and you know that, so suppose uh, for first constructive interference m is equal to 1, so this will be just lambda, right? So first fringe pattern will observe, first uh, bright pattern you will observe is will be at lambda d by d, right? So, and this is also the distance between the between two fringe patterns called beta. Okay, so this is a useful formula. And yeah, now one more thing I want to discuss here, and that is Fresnel biprism. But let me see if there is anything else is needed in M double slit experiment. So yeah, that is all. Maybe if anything else is needed, we will get back here and do the calculation for that. So now Fresnel biprism. So last couple of lectures I was discussing about prisms, and so this is one of the application of prisms. So this is biprism. Okay. So Fresnel biprism is a thin double prism, like so double prism like this. Okay, and if you have a source of light here, suppose S, and it's emitting light in all direction. So let's take the two rays of light, one like this, another like this. Similarly, let's say take one like this for the lower prism, and one like, sorry, like this. Okay. Now we know that prism, what prisms does is they deviate the path of the light. So, so suppose this here, this light will become straight. So this is the axis. Here you have a screen, and suppose this light ray become parallel to the axis, goes at O, and this one will deviate like this, like this. It will go somewhere here. Okay. And Then this will go deviate like this and go somewhere here, and this will become parallel to the axis. Okay, so now you see uh, these two lights. So suppose this is N, this is R. Okay, and they will look. It will look like they are coming from these virtual sources S2, and if we extrapolate this, it is S1. Okay, so now, and also since the path length is different for these two uh, different source of light, virtual source of light. I mean, the light ray coming from these two virtual sources. So there will be a diffraction in this region from O to suppose it's called OP, and this is called the illuminated region of the Fresnel prism. And you can calculate the same things here, constructive and condition for constructive and destructive interference. But the main thing that uh, the most important thing that we have here is the expression for fringe width, which is given by the same formula as above, lambda d by d. So here d is this distance between two virtual sources, and d is this distance. Lambda is the wavelength of the light, and beta is the fringe width. Okay, so and from here you can calculate the wavelength, which will be just d beta by d. And so if you know the distance between the two virtual sources, you can easily calculate this, and you know the fringe width, and you know this distance, then you can calculate the wavelength of any light. So this experiment can be done in a lab, and wavelength of any light can be determined using this experiment. So it's a very nice experiment. Also, one more thing that uh, can be done here is uh, you can also you can also determine the distance between these two virtual sources d by using two convex by using a convex lens. So how you do it is that, suppose kept space here. So okay, maybe this I will discuss in the problem. There will be a problem, and there I'll discuss how we can measure this distance d between the two vector sources. Okay, so for now let's keep these formulas in mind, and let's go to the problems that we have. Okay. So the first problem, uh, it's a simple statement. So the main principle used in interference is there are four options: Heisenberg uncertainty principle, superposition principle, quantum mechanics, and Fermi principle. So I just showed you that this interference is based on the superposition principle. So this is the correct option, B. And okay, that's it. Then let's go to the second problem. Uh, so here, when two waves of same amplitude uh, superpose constructively, the resultant intensity becomes. Okay, now, so suppose we have two waves like this. Okay, okay, they have the same amplitude here. Okay, and they are superimposing constructively. So that means the phase difference is either 0 or 2 pi. So in that case, uh, so what will happen is that the amplitude will become just double, to be 2, and intensity, is given as is proportional to the amplitude square. So for each of these waves, the intensity is k square, ka square, right? And since the amplitude becomes double, so this is the resultant amplitude. Uh, so it will be amplitude is 2a squared. So finally you have k4a square, right? So intensity becomes 4 times. It's also a simple problem. Now let's go to the third problem. Here uh, the question is, zero order fringe can be identified using there are four options: white light, yellow light, violet light, monochromatic light. So as I mentioned during the uh, when we are using when we are doing these YTAC experiment, you have the source, then there is a screen here, and the two light with different phase difference uh, come and constructively or destructively interfere on this point P. But uh, the center the path difference is same between the two lines, and so there is always constructive interference here at all, right? And at all the other points there will be either destructive or constructive interference based on the path difference or the phase difference between the two lines. Now suppose we are using a white light. Now white light is made up of seven different components, or seven different colors of the rainbow, right? Fibcure. So at the center, all of them will have the same phase difference, part difference. So the center fringe will be bright or white in color. Okay, but at other distances, since uh, this lambda depend this uh, this path difference depends on I just showed you the formula, right? So delta depends on lambda here, m lambda or m plus half lambda for destructive and constructive. So for different wavelength of light, uh, wavelength of light, the position for constructive and destructive interference will be different, and hence at all the other place you will get a mixture of different colors. So only the center zero order fringe or the center fringe will be white. So in this way you can identify uh, the zero order fringe using the white light. Okay. So yeah, that is the concept behind it. Now, fourth problem. So here we have the wavelength of the light used in Young's double slit experiment is lambda. The intensity at a point on the screen where path difference is lambda by 6 is I. If I naught denotes the maximum intensity of interference, then the ratio I and I naught is. Okay. So here many things are given. So first of all, uh, the amplitude uh, no, sorry. Yeah. So so first of all, if the path difference is lambda, then phase difference uh, is 2 pi, right? So path difference is equal to lambda, then phase difference is 2 pi. So for path difference of delta by 6, the phase difference delta phi will be 2 pi by 6, which is 60 degree, correct? And so uh, and also you have the resultant amplitude formula given by uh, a1 square plus a2 square plus 2a1 a2 cos phi, right? For two waves, this is the resultant amplitude formula. And since we know that cos phi, so this phi is 60 degree, we can so this is the phase difference essentially. You can write it delta phi also, but I am writing only phi. Okay, so cos 60 is half, and since the amplitude is same between the amplitude is same of the two waves, what you will get is a square plus a square plus a square is equal to 3a square, right? So amplitude squared is 3a square, and we know that the intensity is proportional to amplitude square, so proportional to 3a square. Now maximum amplitude will happen, the maximum amplitude will be just simply uh, 2a, right? Or you can see from this formula, when this cos is 1, cos phi is 1, that is phi is 0 degree. So then you will have a square, 2a square and 2a square from here, 4a square, so just 2. So the maximum amplitude is just the addition of the two individual amplitudes, and so I naught is just k. So this is the amplitude. So uh, 2a square, which is 4ka square, correct? So the ratio I by I naught will be simply 3 by 4. This divided by this. Here you can write I as k3 square. K is just a constant. Okay, so or 0.75. So this is the correct answer. So this was a simple problem. You just have to know how to convert the part difference into phase difference, and the result, and how to calculate the resultant amplitude. Okay, so next up we have another question on Young's double slit experiment. So the question is, in the Young double slit experiment, if monochromatic light used is replaced by white light, then so just uh, the previous in a previous problem we saw that if you have a white light, what happens is that the central fringe becomes white, and all the other fringes are colored, right? So, so here the options are: all fringes become white, not all fringes are colored, no, no fringes observed, no fringes will be observed, and then only center fringe is white and other fringes are colored. So this is the correct option. Okay, this was a simple problem. Then we have another problem. So the light waves producing interference have their amplitudes in ratio 3 is to 2. Okay, so we have, sorry, we have amplitudes in the ratio 3 is to 2. Uh, so we can write A1 as 3A, A2 as 2A. So, and then the question is the ratio of maximum minimum intensity ratio of maximum and minimum of interference fringes. So first we need to calculate Imax. So Imax will be simply uh, let me first calculate the A max and A minimum, then we can calculate it. So amplitude, maximum amplitude will be just A1 square plus A2 square plus 2A1 A2 cos phi. So when the cos phi is 1, then we have the maximum amplitude, and since A1 is 3A square, so 9A square, then 4A square, and plus 2 into 3 into 2, which is 12A square. Okay, and this is 25A square. So this is the amplitude maximum, and intensity is depends on the intensity is just proportional to amplitude square, right? So the intensity maximum will be proportional to 25 A square. And similarly, A minimum will be when this cos phi is 0. Sorry, cos phi can go negative, so minus phi. So minimum will happen when cos phi is negative, minus 1, right? In that case, we will have 98 square plus 4A square minus 12A square, which will be just so A square, and hence I minimum will be A square minimum which is just A square. So I max divided by I min will be 25 by 1. So 25 is to 1 is the ratio of maximum and minimum intensity. Okay, so this is also simple. Then you have then we have this seventh problem. Here the question is, in a Fresnel biprism experiment, the fringe width 0.5 mm is observed on a screen. So here beta is given, which is 0.5 mm. Okay, and distance d is given 2 meter from the source. When a convex lens is placed between the source and the screen for two positions of the lenses, the images of interfering sources are produced on the screen. Okay, the separation between the two images is found to be 4 mm and 1 mm respectively. The wavelength of light used is. So now here we don't have the distance between the two virtual sources, but we are given another information that the separation of two images formed when we place a biprism like this. So suppose these are our two virtual sources, and here we have put a convex lens, and if we vary the position of convex lens from here to here, what will happen is, so suppose first in the first position uh, we have light ray coming like this, and it will form an image here. So let's draw it more clearly. Uh, just wait a minute. Yeah. So I'm bad at drawing. Yeah. So this is the biprism. This is suppose your S1, source 1 and source 2. We have to find this distance, d, right? And this is our original source, and this is the axis. Now at some point there will be a light uh, so these two lights are passing like this. Then you have another one passing like this. Okay, and if you place a convex lens in this position, this will converge the light like this, right? So you'll so you'll get an image like this, a circle like this. Okay, and if you move the position of this lens to suppose here, then the convergence will be less, so you will get a circle like this. And suppose this distance is u, and this distance is v, and then this distance for the second position is u prime, and this is your v prime. Okay, and suppose this circle, the diameter of this circle is d2, diameter of this circle is d1. Then you can write d1 by d, sorry, equal to v by u, and d2 by d equal to v prime by u prime. Okay, and so from these two formula, uh, uh, you can write simply d equal to d1 d2 square root. Okay, so you have the distance between the two sources as an square root of uh, these uh, a square root of the two images formed, of the separation between the two images formed on the screen, which is d1 and d2. So here d1 is given as 4 mm, and d2 is given as 1 mm. So from here you can find the uh, separation between the virtual source, which will be just 2 mm, correct? And then you can easily calculate the wavelength of light uh, by this formula, beta d by d. So beta is 0.5 mm, d is 2 mm, and this is 2 meter, the capital D. So 0.5 into 10 to the power minus 3 into 2 into 10 to the power minus 3 to convert into meters, then 2 comes. So you will have 500 nanometer is the wavelength of the light. Okay, so this this is how you can calculate the distance between the two sources using a convex lens. So now we have this fifth problem, which is the distance between two coherent sources produced by a biprism is 1.0 mm. Okay, so here d is given 1.0 mm, and when the distance between the source and the screen is 0.9 meter, so the capital D is given, and the fringe width obtained is 0.12 mm. and okay, and when if the screen if the distance is 1.8 meter, then we are asked the fringe width. Okay, so it's a very simple problem. Uh, so first we have to calculate lambda. Okay, so lambda is, so suppose this is d1, this is d2, this is beta 1, this is beta 2. This is unchanged. Okay, and lambda is beta d1 by d1, which will be also equal to beta d2 by d2, right? So here b, beta sorry, beta will also be different, beta 1, beta 2. So we know beta 1, d1, d2, sorry, and d1 and d2 is same. Yeah, okay, so this will get cancelled, and d2 will be beta 1, sorry, d2 will be beta 2 by beta 1 and into d1. Okay, oh sorry, we have to find beta 2, so beta 2 will be beta 1 d2 by d1, and beta 1 is given as 0.12 mm, that is 10 to the minus 3 meters, into d2 is 1.8 meters, and d1 is 0.9 meters. So this will just do, and 0.24 to 10 to the power minus 3 meter. Okay, so the answer is 0.24 mm. Okay, so you see how many things we can calculate with this simple formula of uh, Fresnel biplanar. Now the ninth problem. Here we have this question. If a thin sheet of refractive index 1.5 and thickness 4 mm is placed in the path of the light, then the additional path difference introduced is, okay. Now suppose this is a thin sheet. Okay, its refractive index is 1.5. Light ray is passing like this. Now since uh, the the light ray will suffer uh, reduction in its velocity inside the this sheet, the optical path length will be reduced, and we know that the optical path length And we know that the optical path length uh, is given by uh, so suppose this, if this is the thickness of the thin film, the path length is given by refractive index into uh, the thickness of the sheet. So the path difference introduced will be just uh, in t minus t, right? So this one, and refractive index is 1.5, thickness is 4 mm. Let's keep it in. So just zero point 0.5 into 4, that is 2 mm. Okay, so this is the additional path length that will be introduced by this thin sheet. So instead of 4 mm, the light will have to travel 6 mm. Okay. Then 10th problem. Uh, in Young's double slit experiment with monochromatic light, how is fringe width changes if the screen is moved closer to the slit? So we know that the fringe width is given by lambda d by t, right? And if the screen is moved closer to the slit, that is d, d is being reduced. So, and it depends linearly, so beta will also decrease, right? So linearly decreases. So simple problem. Then another simple one. In Young's double slit experiment, light of violet, yellow, and red colors are successively used. So if beta V, beta Y, and beta red are the fringe widths for violet, yellow, and red colors, then which of the following is true? Okay, so now, as I told you, beta depends on lambda, right? Directly proportional to lambda, and we know that red has uh, highest wavelength, so lambda of red is greater than lambda of y, which is greater than lambda of violet. So violet has the shorter wavelength. So then uh, beta will also behave same. So beta of red will be higher than beta of yellow, and it will be higher than beta of violet. Okay. So the correct option is B. So very trivial question. Now the last problem for today's session. So here we have in Young's double slit experiment, the two slits are made 2 mm apart and a screen is placed 1.2 meter away. What is the fringe width for light of wavelength 4800 angstrom? Okay, so here the distance between two slits is given, and the distance between screen and the slit is given, which is capital D, and wavelength of light is given, which is 4800 angstrom, which we can write as 4800 into 10 to the power minus 10 meters. Okay, so fringe width we can calculate using the formula lambda d by d. Okay, this we can write it as millimeters like this. So 1.2 into 4800 into 10 to the power minus 10 divided by 2 into 10 to the power minus 2, and so we can just oh, sorry, this will be 2400, and if you calculate this, it will be 0.288 mm. Okay, so yeah, uh, this is the last problem, and we dealt with very simple problems with today regarding interference and Fresnel biases. So see you guys in the next live session.